to have Chef Rory Barnes going to talk about FILLET, and which is really focused on those specific models. The floor is yours, Rory.
Great, thanks so much, Thomas. So let me just share my screen here. So full screen, are we good? I just need to,
Yes, sorry, I was muted.
well, I'm gonna just go with all of you on the side here. All right, yeah, so thanks, Thomas. Really happy to be here. It's a real privilege, of course, to be the new chef for FILLET. Thanks, Thomas, for the invitation. And really looking forward to see where this effort goes in the future. So before I do get started, though, I do just need to reiterate what Thomas said at the beginning of the day, which is that Russell Dietrich did an amazing job getting this project off the ground. Really just couldn't imagine trying to take this over without all the great foundation that he put together for us. So as just so you know, so Russell had been at the University of Victoria, but he's now taken a permanent position at the Canadian Centre for Climate Modeling and Analysis, still in Victoria, but now really focusing on the Earth. So the good news is that he is still going to be involved with FILLET, so it's going to be hopefully a fairly painless transition, and I'll be able to pick his brain on various aspects of where we've been so far with FILLET. Also want to thank everybody else whose name is on the screen here. They all represent different EBMs that are being applied to exoplanets today. So we're going to see some results for some of these groups. Obviously this is still a work in progress, but obviously huge thanks to everybody who has contributed to FILLET through the years. So I wanted to start by just kind of reviewing the energy balance model concept. I know a lot of you don't work on energy balance models, and some of you are also just new to the cuisines family. So just thought it'd be helpful to spend a few minutes just going over some of the basics here. So an EBM is basically a one-dimensional climate model in latitude. It has its origins back in the late 60s. But I highlighted that North and Coakley paper from 1979, as I've kind of been getting up to speed on this over the last month or so, and I've been looking more carefully at what the other EBMs that are out there have been, how they've been derived. North and Coakley is really the starting point for all of them. So if you're interested in just going back and reading a classic paper, I'd recommend that one. That really is the foundation for all of the modern EBMs that are being applied to exoplanets. So it is a one-dimensional model, so that means a lot of the physics is approximated and or parameterized. So that's a good thing and a bad thing, as we'll get into today. But obviously, it's a highly simplified climate model. And I think it maybe goes without saying, but ABMs were sort of the precursors to GCMs. So you can sort of think of GCMs as extremely sophisticated EBMs. And but basically, it all boils down to a single equation. I don't usually show equations in talks, but I think in this case it's valuable just because it helps to see what's the physics that is going on in these models, and to think about too, what are the parameters, because that really does influence how we go about designing a protocol. So the key variable in all of this is surface temperature. Probably not too surprising. That's what we're trying to fit based on other parameters. And so some of those other parameters are the heat capacity. And this is where things start getting interesting as we parameterize them, because of course this is one-dimensional latitude. So we're trying to combine oceans and land, and that can include deserts, forests, mountains, ice. All of that can go into a single latitude. So this is where we start seeing the difficulties in approximating and parameterizing the climate, but nonetheless, we can do this. Heat diffusion is this important concept here about just how efficient is energy transported between the latitudes. So again, this is another parameter that has to either be tuned or an assumption has to be made about it. Then we move on to the outgoing long wave radiation, the radiative cooling of the planet. And then, of course, there is the input, the installation or insolation if you're studying the Earth. And finally is the albedo. And again, just like with heat capacity, the albedo is this process this parameter that needs to somehow be fit to compensate for all the different forms of surface features that are on a planet. So this is the basics of what we're doing. This is the one equation that we use. But what's key here also is that it's actually spread out across the planet, right? So in general, with an energy balance model, We're going to divide the planet up into latitudinal bins. I can tell you that for vPlanet, we use about 150 latitudinal bins. I don't know what everybody else uses, but it's around that range. It gives you pretty accurate results in terms of reproducing the Earth's climate. You can make some decisions as to how you want to look at these individual latitudinal bins. In our model, we have two bins, one for ocean, one for land per latitude, but I know others mix this all up into a single bin. And for each of these latitudinal bins, you then have to assign a temperature. Alpha, if you remember, was the albedo. And so each of these bins records the temperature and the albedo. And then, of course, you have input, the installation, or sometimes called the shortwave radiation that comes in, warming the planet. And of course, you worry about things like the zenith angle. You try and do all the geometry right. And then you have emission from each individual cell. So this is the basic framework that we're trying to solve here. So you can sort of see how it's sort of a precursor to GCMs. And so in this most simplest form, this is what we do. And oh, I'm sorry, I forgot one more thing. Yes, the heat diffusion, of course. So we also have to think about how the energy is diffusing between the cells. And then we have to simulate this to equilibrium, at least in most cases. In the simplest way we think about EBMs, we simulate to the equilibrium. If you're being really conservative, that maybe takes about 1,000 orbits. You get really close, I think, after about 100, but you simulate to 1,000 orbits, you're pretty much there. With vPlanet, the model that we use in my group, that takes on the order of 5 or 10 seconds. So pretty fast to get to equilibrium. So with that in mind, let's talk about some of the advantages of EBMs. So the number one thing I think is computational efficiency. It's one equation, maybe you've spread it out over 150 cells, but nonetheless, this is in modern computing an extremely fast kind of computation to make. And that allows you to simulate extremely long-term processes. Obviously, thousands of years is trivial. Millions of years is easy. That can be done in just an order of minutes. And so in principle, of course, we can also get to giga-year simulations. I'm not aware of anybody who's used an EBM to simulate for billions of years, but if anybody does know, please let me know. We're just starting to think about that. I think that's sort of the new frontier. I think in EBMs is really getting into the evolution of planets over the age of their system. And then the other way you can think about this to leverage this computational efficiency is through large parameter sweeps. And you're going to see later that that's what really that's really what we try to take advantage of in FILLET. Another advantage is it does have more horizontal information than some of these RCEs, or these radiative convective equilibrium models that just have one dimension and altitude. Of course, the flip side there is that EBMs don't resolve the altitude or resolve the atmosphere. But you can at least think maybe that's in some cases this is an advantage to have more horizontal information. And because they are relatively simple models, I think another advantage is that it's pretty easy to program to code up these kinds of models. Certainly compared to GCMs, it's certainly much easier. Some of these advanced GCMs have millions of lines of code, whereas a simple GCM can be put together in just a few thousand. It also means that you can quickly adapt your code to newly discovered planets or just new ideas, anything you want to test out, that can be done pretty quickly. And of course, you can also couple EBMs to other physics, and we'll talk about that here in the next slide or two. So you can, because it is relatively simple, you can think about coupling it to like interior modeling, like what Tim just talked about, or orbital dynamics, or stellar evolution, etc. So let's talk about these additional physics. What else has been done in terms of how we've been able to advance EBM modeling over time? Well, I think the first thing that people really started to do was to add the growth and disappearance of ice sheets. So this, of course, affects the albedo, but it's also really important for the overall climate budget of a planet to think about, are you getting ice sheets on land? Are you getting sea ice? Because that does dramatically affect albedo and surface temperature. Some people have started to add in biological feedback. So sort of as a climate in a cell changes, what is the life on that planet, like are there forests there? For example, that could change the albedo. In particular, the ESTEAM group based in Trieste has been working quite a bit on this. There's also people thinking about clouds, the bane of most climate models, but we are getting some cloud physics going into EBMs, starting with, again, so the ESTEAM group with Biasiotti et al. 2022, and then Ramses's model is also including clouds. I don't want to overstate the value of these clouds. I mean, they are still difficult to include, but I think there's been some great progress starting to get clouds into EBMs in a realistic way. Additionally, there has been work looking into how carbon cycles affect the long-term evolution of the atmosphere. You can see there's a handful of papers that have looked into that. And then there's also some work that's been looked at that's focused on how orbital dynamics affects EBMs. So these latter cases are ones in which we're not going to just simulate to equilibrium, but we are going to perform long-term time evolution simulations on the orders of, in these cases, on the orders of millions of years, to look at sort of how the climate could evolve due to these other effects. Of course, with every advantage comes a disadvantage. I guess Tim said we've all seen this figure a lot in the previous talk, so I guess we really do see it a lot. But just credit to you, Sonny, it's a great figure. So some of the disadvantages or limitations, I should say, of EBMs are that we are limited in terms of the composition of the atmosphere and what we think they can be made of. We do tend to think of this as being only really applicable to planets in the habitable zone, terrestrial planets in the habitable zone. They really need to only be applied to rapidly rotating planets. And I put usually there because some clever people are starting to think about how we can basically flip EBMs on their side, literally. So like Jacob Hock-Mizra has been working on how to transform his EBM into one that will work for tidally locked planets. And of course, as I mentioned before, there's numerous parameterizations. So everything is very simplified, and it's not always obvious that you're getting realistic results out of the EBMs. And so I want to also talk a little bit about this issue of how we handle the atmospheres. So of course, in reality, there are layers in the atmosphere. They absorb light, they emit light. Eventually, some of the light will hit the surface, which might be land, it might be ocean. These are features that are resolved really well in GCMs and RCEs. They often can even resolve the spectral wavelengths. And GCMs in particular can also resolve the surface quite clearly. So those are definitely strengths of those models that don't exist in most EBMs. Instead, we just have this sort of slab atmosphere surface kind of treatment in EBMs. So in this case, what we have to think about it as how do we actually realistically model radiative transfer in the atmospheres. This really boils down primarily to the outgoing long wave radiation. We need to understand how the atmospheres cool, and then on the flip side is also clouds. How do atmospheres reflect the light? So these are challenges for how we manage to model the energy on these EBMs. Is just how are we going to treat this monolithic slab of a ocean, of an atmosphere and land, and actually try and believe that we're treating the radiation correctly. And there's different schemes for how to do this. I'm just going to show you a quick example where, well, maybe not so quick. I know this is a bit of a complicated slide, but basically these two figures show you what some different parameterizations that have been applied to different energy balance models through the years, and many of these are involved in the protocol. So we're looking at the outgoing long wave radiation on the vertical axis and surface temperature on the horizontal axis. The left is for basically pre-industrial Earth, and then on the right is for this very carbon dioxide enriched atmosphere. And the different curves show you some different parameterizations that are out there in literature. And on the left, where we are pretty well anchored to Earth, we see most of the models fit pretty well together. Until you get to maybe 325, 350 degrees Kelvin, then we start to see some divergence between them. But nonetheless, we think then that at this sort of level of CO2, we have a pretty good prescription for the atmosphere. But things get a little more complicated at 5 bars, where these different parameterizations have different predictions. To avoid this, some EBMs actually just avoid this sort of polynomial fitting and have incorporated large lookup tables that interpolate results from other sort of more line by line type calculations for the OLR. So different schemes, and so these are of course the kinds of differences that we'll be testing with FILLET. All right, so moving on, that's your maybe somewhat extended review of EBMs. I want to just tell you where we're at right now next. So I sort of see this process, this exomit process in 4 stages. I think Linda covered this pretty well this morning. So, but right now we've basically finishing 1 and 2. We've been meeting for a few years now, at least 2 years. We have been developing a protocol, and now we're in the process of gathering the results from the different codes. And hopefully soon we'll get to stage 4, identifying the differences and squashing the bugs. However, it's never quite that easy. We did, in fact, as we were gathering results, Russell realized that there was some issues with our initial protocol. And that was just because there were some differences between how different groups were running their models and how they had been defined. And so we do have a protocol 1.0 paper that came out a year ago. And now we're in the process of revising that to a version 1.1. So Russell showed me the draft of this the other day. It's in really good shape. I'm expecting that he's actually going to finish this and still be the first author, even though he's no longer going to be the leader of the group, but he's already 99% done with this. So some small changes, and you'll see that reflected in some of the results that I'm going to show you in the next few slides. So I'm going to just quickly review this protocol version 1.0 that we came up with. And it's described in this paper. You can go read it if you want, so I'm just going to touch on it briefly here. We identified 3 benchmarks. So these were kind of simple simulations that are just sort of meant to kick the tires on your model, so to speak, just sort of see what kind of results you get. So the first one is looking at the pre-industrial Earth. And one thing we noticed with EBMs is that because there are so many parameterizations, we tend to calibrate our models to the pre-industrial Earth. And so basically the first benchmark we asked people to do is just to make your model reproduce the pre-industrial Earth. We didn't really care what you had to do. It was just sort of, what do you have to do there? And most people had already done this. And then benchmarks 2 and 3 were about prescribing specific parameters to all be uniform amongst all the different models and then seeing what the results were. And we looked at a high obliquity and a low obliquity case for those 2 benchmarks. Then we had 4 parameter sweeps, or I should say 4 experiments that constituted parameter sweeps, of planetary climate. So these were much more involved than just the benchmarks, which were just sort of a single simulation. So they're really sort of in 2 groups. There's looking at planets around G-dwarfs, like an Earth-like planet, and then starting with either a warm planet, no ice on the surface, or a cold planet, completely covered in ice, and looking at how the climate evolved to equilibrium in those cases. And then the experiments 3 and 4 were to look at this hysteresis feature that I'll show. If you're not familiar with this, we'll get to it in a few slides. But just looking at how sort of climate responds as you warm it up or cool it down. And in the first protocol paper, we had 2 different codes, vPlanet's Poise module, that's what Russell and I worked on, as well as Esteem, this code based out of Trieste. So moving on, so here's some results from benchmarks 1 through 3. So looking at the pre-industrial Earth and low obliquities. So on this first panel here is some results from the vPlanet model. And you can see that, so remember benchmark 1 was just tune it to the Earth. And then benchmark 2 was basically the Earth, but with prescribed amounts of land and water and a certain amount of CO2, et cetera. And so you can see that there are some differences here, but in general, things are looking fairly well behaved. And then there's also in benchmark 3 was looking at 60 degrees, and now here's the other model that participated in the protocol 1.0 paper, Esteem, where we see that it's looking pretty reasonable again. But of course, we don't have ground truth for a planet like this. But we do see at least here that it's colder at the equator, which is what we expect. Moving on to the experiments. So now we're moving into the parameter sweeps. So we had the two that I talked about, the warm start with an obliquity, and it's an obliquity installation sweep. So here's one of the examples here, again from BPlanet, where just so it's easier to see what we're talking about here, these different colored regions represent different surface types. And so we see that there is this interesting kind of distribution of where the ice is on these planets as a function of the installation and the obliquity. And of course, we were all really, at least I was relieved when we got the results in from Esteem, and it looked qualitatively similar, different resolution in terms of the parameter space, but we're seeing ice caps and ice belts in the same locations, and the shape of the boundary between ice-free and snowballs were also looking similar. And then looking at experiments 3 through 4. So remember, these are these hysteresis maps, or sometimes they're called bifurcation diagrams. They look like this, where we're plotting the ice line latitude. So this is what is the extent of a polar cap. And so in the BPlanet version of the EBM, there's land and ocean cells, as I mentioned earlier. And we see basically, this is sort of the classic bifurcation diagram where when the ice line latitude is at 90 degrees, the planet is ice-free. When it's in between 90 and 0, there's an ice cap. When the ice line latitude is at 0, that means your planet is in snowball. And of course, there are these unstable regions where you can make these quick transitions. And the cold start planets are those that start covered in ice, and the warm start planets are those that start free of ice. And then as we vary the installation, we then see these results as to what happens to the climate. I also had the bifurcation diagram for CO2, but I'm not going to show that here, but I will get to it in just a couple slides. So I want to then move on to gathering the results. So we've been getting results from various groups, and these are figures that again have been made by Russell. I haven't been able to get to this yet, but you can see that we now have 4 different EBMs that have contributed data. So benchmark 1, as you remember, was the pre-industrial Earth. Tune the model to reproduce the temperature of 288 Kelvin, and we see that they are qualitatively similar. Certainly, the temperature looks very similar, as we might expect, because that's what it's really designed to reproduce. But we do see some pretty significant differences here as well in the terms of the albedo, especially. So some similarities, some differences. So it'll be interesting as we dig into this as to what's going on in the different models. And I just want to mention, I do have new results from Awoma Shields group, thanks to Vidya. But unfortunately, I just got those last week and haven't had a chance to process them yet. But obviously, the group is still active, and we're making progress. And then moving on to benchmark 2, pretty similar results, as you might imagine, to benchmark 1. We are seeing, mostly, here we see differences in the temperature, though, now, right? I mean, because we're not really forcing it to show modern Earth's temperature, we see a wider range in the temperature as a function of latitude because of the different assumptions of the different models. So, yeah, again, qualitatively similar, but we see, larger variations. And then here's benchmark 3, where we see even some larger differences. And so, again, somewhat similar in temperature, except we do see poise is the BPlanet poise module is quite a bit different. And the OPS model also has some differences as well. So, we have some work to do to try and figure out what these differences are, but certainly interesting to see these results. See, I'm starting to run low on time, so I'm going to speed up a little bit here. So here are some results from the experiment 1 with the warm start. Just focus on the right column for here. You see that we've now we've gotten rid of that discrepancies between the resolution and the parameter space. And so you can see that some of these are looking similar, but some of them look different. In particular, the third row, esteem, looks quite a bit different. And that's actually because of the issue with our definitions of the first protocol. We didn't realize at the time that we needed to specify two ice lines in order to capture ice belts. And so I have those new results from Paulo, but again, I don't have those to present today. And then for completeness, here is the cold starts. And so again, it's somewhat similar between some of the models. So especially Poise and Hextor look pretty similar, but the others seem to be quite different. And again, I do have the new results from Esteem, but haven't had a chance to look into it yet. So yeah, due to time, I'm going to kind of skip through this pretty quickly. So here we have, just for completeness though, here are some of the bifurcation diagrams. This was for installation, so seeing some similarities, but also still some differences. And again, also, and then when we varied in terms of the CO2 pressure, we do see some differences. I had a note on the previous slide. One thing that's fundamentally different about OPS is that it actually doesn't assume a constant heat diffusion between all the cells. In fact, it allows that to be calculated on the fly. So that might be one of the differences why it's looking a little bit different in these cases. So based on those results, we've modified the protocol version 1.1. So this is what we're going to be submitting this soon. And I wanted to make this point here at the bottom that if any of the other groups run into a similar situation, what Planetary Science Journal asked us to do was not to submit an erratum, but actually to create a whole new paper. So maybe your experience will be different, but that's what they asked us to do. And so looking ahead, just want to let you know that the current steps are to finish this new protocol paper, finish gathering the results from all the other EBMs, and then we're going to start, hopefully in the next year, start writing a paper that actually does all these comparisons. One thing I want to focus on this year is identifying observables. In the protocol 1.0 paper, we did not actually do that. And as Linda mentioned this morning, that should be part of our protocol. And I'm also looking forward to working more with GCM folks and thinking about how our results can leverage, how we can leverage each other's results. All right, so that's it. If you are interested in anything more to do with EBMs, please let me know. If you know of anybody that is using EBMs and is not part of FILLET, please have them get in touch with me. And so I will stop here. Thanks so much, everybody.
Thank you very much, Rory. That was a great talk, and that's such a lot of work from that team. So it's super impressive. Thank you about that. And yeah, thank you for mentioning what you said about the version of the protocol. We have the same thing with Samosa. Tomorrow, Jacob Akmistra is going to talk more about it, but it's really part of the process to have indeed the protocol first and then digging into the results. I have the good advantages, as Linda mentioned this morning, but sometimes, yeah, we found out after things that we would have needed, and then we can revise the protocol. It's really like, lab experimental protocol kind of way. So
Yeah.
So yeah, we have a couple of comments. We have Jacob said in the chat that he has done some giga-year calculation with an EBM, and that's to be published. So
Great. Well, I'm looking forward to that, Jacob. And I guess I know why I haven't seen it yet because it's not out yet. So yeah, so like I said, that is the frontier. I think we're getting to these long-term simulations, so that's great. And let's see. And so Emmeline asked about when is a good time to join FILLET with a new EBM? Now. Now is a great time. I mean, we're still getting started. And I think getting involved now will help you to kind of start thinking about how to benchmark your own EBM against what's been done so far. So yeah, if you're working on that, Emmeline, please join us. And then yes,
join as well the Slack channel if needed. So yeah.
Yep. Any other questions? I know we're past time here though, so we want to just move into discussion. I understand.
No.
All right. Well, thanks everyone.
Thank you again, Rory. Thank you.